It's a great pleasure to introduce our today's speaker, Rama Chellappa, who many of you know is a Bloomberg Distinguished Professor with joint appointment across electrical and computer engineering and biomedical engineering in Homewood. He's also the chief scientist at the Johns Hopkins Institute for Assured Autonomy. As a lot of you know, that he's actually a pioneer of AI method. He has been working on this area for more than 4 decades, has made foundational contributions to computer vision problems, biometrics problems, as well as automation of card to the forensic problems. And he's obviously received many awards I'm not going to name. The only few I'm going to mention is his recent election in the National Academy of Engineering, but also the Jack S. Kilby Signal Processing Medal from the IEEE. And since he has been arrived, we were very lucky to steal him because he was at University of Maryland for 29 years, I believe. And he was at various times, he was chairs of electrical and computer engineering, center director of automation. And so I think he joined a few years back, and as we have seen, like, has been so active in the data science and AI initiatives. And I have been very fortunate to get to know him from very early on, like Dennis first introduced me and told me to work together. And since then, I've enjoyed a lot of conversation. And one thing I really liked about talking to him, like, he comes from a computer science background, is that he appreciation of statistical thinking. And that's what he's going to actually, I think, talk about as well today. Without that, without further ado, Rama, yours.
Good afternoon. Happy to be here. I got my PhD from Purdue University in 1981. While I was a student in electrical engineering, we didn't call it electrical computer engineering at that time, just electrical engineering. I also took half a dozen graduate courses in statistics department at Purdue. At that time, at least, maybe it still is, a very strong decision theory school. Shanti Gupta was the chair at the time, and it had people like Professor Pillai, with whom I studied multivariate statistics. And then, non-parametric statistics folks, Premis Puri, some of you may know, a stochastic process. Herman Rubin was there. He was a nightmare. Students taking classes with him, tough exams. So, of course, you will wonder why, I'm so interested in statistics. I always say I'm an Indian. I grow with large population. So what other field attracts me than statistics? And I also like giving this talk in particular because I took half a dozen graduate courses, and there were just too many homeworks and exams from these stat professors. So I said, once in a while, if I can give them some problems that they can probably work on, I kind of get some revenge back, right? So that's what this thing is about. Okay, now let's see how I navigate.
Just on your computer.
Yeah, no, I think, there you go. Sorry. So I'm going to talk about deep learning, AI a little bit, not a whole lot, and then how it's used for computer vision. Computer vision has two major statistical applications, regression and classification. If you take computer vision, that's basically what computer vision is all about. So definitely it's a statistic. The one thing that computer scientists always had some issues with statistics is that computer vision is also dominated by geometry. So, we have objects, right? Objects have parts, and how parts are put together. Some of the parts could be articulating if you are looking at a human motion and so on. And, statistics and geometry, it was a little bit harder, right? On the other hand, you see statistics and shapes. You have people like Kanti Mardia and others working on that. So usually folks who have a background in electrical and computer engineering, when they work in computer vision, they will bring statistical methods. Whereas CS folks, purely geometry, not, it's a very crude approximation. But statistics has a role to play wherever there is data is. So we'll talk about that. And I'll talk about what I see are the issues with the deep learning and AI these days, as AI is very much dependent on the data. And, we need a trusted deep learning and AI. And I think that's where statistics come into play. You are the custodians of any method to tell us, how good that is. You estimate bias, you estimate variances, you give probabilities of error, provide confidence bands, and so on. So, and then I'll briefly go over the 9 problems. So who am I? Very quickly, I took statistical pattern recognition in spring of 1977 at Indian Institute of Science. I immediately fell in love with it. So I came to Purdue. At that time, Purdue was the world's best place to do pattern recognition. Fukunaga, Kingston Fu, and Cashier, my advisor, was out there. And so I got into, various courses. Pickle and Doxum was a new book at that time. I think it's still being used. Gary Brieb used to sit, and that's the book I had for my first course on mathematical statistics and so forth. And, there are all these things that are mentioned here, great researchers in statistics that I learned from. Actually, Jim Berger was at Purdue at that time. He used to talk about Stein effect in every which way he was using it, right? So, and then I got interested in representations of images. Now you are hearing about generative AI. I worked on Markov random fields as a generative model for characterizing images, and then using that for various purposes, synthesis, classification, segmentation, and so on. And I was very much inspired by the 1974 JRS Series B paper by Julian Bezak, who I just learned today is advisor of Professor Chatterjee.
Advisor, but he was my professor.
Teacher, your professor. Okay, yeah, that's good. And of course, we did 2D spectral estimation and so on, and developed confidence bands and so forth. So what I learned at that time, where statistics will be useful, is to provide performance counts. So if I estimate the structure and motion of an object that is moving in a video sequence, I want to be able to say how good my motion estimates are, right? So Kremer-Rao bounds, all of that stuff we could do, right? And then later on, we got into representations, object that will allow domain shift. You have a training data, you have a test data, they have different distributions, how you adapt your classifiers to handle the new data. And, there is a nice book by Chikusi, Statistical Inference on Manifolds and so forth. So I've been kind of playing around with these things, and I'm a pretend statistician. Let me be very clear that, I love statistics, but I don't think I fully understand it, but it's okay. Sometimes just the love makes for lack of understanding, right? So neural networks have been around for a long time. It goes back to 1940s. Hebbian rule, that's where it was, the learning rule came for a very simple neuron model. And of course, the universal representation theorem is actually mentioned all the time as why a 3-layer neural network should be good for classifier. They say, this is classic results from Kolmogorov, which says with 3-layer neural network, a mapping from data to label can be represented with any desired level of accuracy, provided you have sufficient number of neurons and so forth, right? So it doesn't say how many. I mean, that is engineer's problem. That's what I love about mathematicians. They say existence, and then of course, you have to prove that such a thing is possible. It comes to engineers like me. Anyway, so PNAS 1982 had a nice paper by Hoffield, which talked about traveling salesman problem. It brought neural networks back into picture again. And there was a lot of excitement at that time. I remember 1987 conference in San Diego. I was at USC, so I went there. We thought 500 people would come, several thousand showed up. So for the next 10 years, we'd build neural networks, 3-layer networks for everything, make soup, make sandwich, make this, make that. It just went on for a while. Suddenly SVM showed up and it beat the performance bound. And so we kind of dropped it and we went there. Anyway, so I worked on all these things and I even wrote a monograph and so forth. And, if you remember the 3-layer network, you have input layer and then you have, dot products, that goes on. And then there is a nonlinear mapping, sigmoid nonlinear, and then it goes all the way to the top layer. And then we try to get the parameters using so-called backpropagation method so that the weights are such that you approximate well what you project as the label with your current values of parameters and what actually is the label. So it's a supervised technique. We need to have data, we need to have labels, the three-layer network, right? Yeah, in parallel, Jan LeCun, who is very well known in this field, he said, I don't want like this, W times X and so on. I just want to have a convolution because in image, convolution is very important. It produces another image. And so he basically replaced, that's where he called convolutional neural networks. His PhD thesis was on that. And in 1998, he had a very good paper where he showed a 5-layer network, could do a good job on OCR problem and so forth. And then what happened, this is his network, right? You start with a character, you go through various convolutions, and he also has put a restriction, translation invariant, so that the number of parameters will not, explode. And then you finally have the 0 to 9 or alphabets and so forth. So when you have a particular weights for these convolutions, from the input, you will go to the output, and that may not be the real output because these are your values of the parameters, but you know what the real output should be. So you adjust the parameters so that they get as close as possible, right? That is the nature of backpropagation, okay? Using stochastic gradient descent and so on. So now what happened? Jan LeCun's work did not get much reception from computer vision folks because that time we were very interested in model-based methods. We wanted to model illumination. We want to model the scene. We want to model the object. And then we want to come up with the methods for figuring out what's inside a video or an image. And this whole idea, you just feed some inputs with labels, and then you figure out a representation and then use it. It was a little bit out of sync, okay? And also, at that time, the results that Professor LeCun had was mostly OCR types of problems, and so it was not clear whether they will scale. So his work was not given much attention. But then right around 2011, 2012, AlexNet came. 2012 is when AlexNet came, which basically takes Jan LeCun's network, adds a few more layers, replaces sigmoid nonlinearity with the ReLU, restricted linear unit function, which is kind of 0 and then poof, linear, and then GPUs. And so at that time, what happened was in computer vision, when I was a student, we didn't have a lot of data. There's no data sets to speak of. There's just one data set from University of Southern California. And so we will just show limited experiments, our results, our things, and everybody was happy. Okay, but then somebody said, we need to have a lot of data to evaluate what everybody is doing and so forth. And that's where ImageNet came. Some of you may have heard about it. It's a large data set, curated object detection, object classification work by Fei Li when she was at Princeton. And so people started experimenting their methods with the data. There were a lot of benchmark workshops and so forth. And then, AlexNet authors tried their method on that data set using an extension of LayNet. It's a 7-layer neural network. It was very good. The error rate went down. That's it. My life changed. Since that time, everybody said, the largest network that you can afford, the largest data set you can have, crank it. So computer vision, in some sense, I know I'm being recorded, but I've been doing this for 43 years. I felt sad because we spent so much time learning the models and the physics and the this and that, and now say, no, you have a lot of data, you have a lot of GPUs, yeah, go for it, you're going to be fine. Well, you cannot argue against performance. Right? It works. It gives best results. Every problem we do in computer vision is now some form of deep learning. In fact, we threw away convolutional networks. They are now in transformers. I'll get to that a little later. It's there at the very end. So that's my life right now. So, big companies which have a lot of GPUs can build foundational models. And so we are waiting and praying that it'll be open source so we can fine tune. Not the most pleasurable situation, but that's where we are, okay? So now we have like 151 layers and all of that. So InceptionNet from Google, ResNet, Kaimeng Hayes work and so forth. But the thing, when you look at it, people say, oh, it is AI, it is AI. I said, wait. It is, in my opinion, a nonlinear hierarchical regression. That's what deep learning is all about. But with no real underlying, theory from mathematical statistics to support that. So it is somewhat troublesome, right? So now, since it is working, if you really see the early days, AI and neural networks were not friends. Because AI was more on symbolic processing, more on domain, not dependent much on data. But now we have gone with all data, it's working, so everything is now AI, of course. So neural network is, deep learning network is a hierarchical network, 101 layers, and it has non-linearities, RADU. It has input with labels, and then we are trying to find the parameters that will give the best output that matches the labels you have with your training data. Now, what is the problem with that? Well, of course, when you do linear regression, you can come up with a lot of optimization things, and you can talk about, confidence band, performance bounds, and all of that. When you have a hierarchical model, it becomes difficult, even for linear. In 1982, I was trying to come up with a representation using time series models for multi-resolution processing. Wavelets were natural for that. So I said, let me think of a time series version. So I start with an AR model. You take the data, you average and subsample, immediately it becomes ARMA. And then afterwards, it stays ARMA. So given an ARMA model at a higher level, trying to rebuild an higher resolution AR model, it's a very ill-posed problem. So right there, I said, when it goes hierarchy, it becomes problem. On top of that, if you add also sigmoid nonlinearities, it becomes a problem. So people are going for larger and larger data sets. And of course, generative models have come, GANs. Now they're being replaced by diffusion models and so on. So vision transformers is a new thing that has kind of been adopted by computer vision. It came from natural language processing. Believe it or not, the underlying intuition for that is the autoregressive model. I tell you, 1977, I come to Purdue. The first problem I work on is model order estimation for AR and MA components. My advisor wrote a paper in 1977, October, automatic control, a Bayesian comparison of empirical models for time series data, automatic control. You all know about Akai case criterion, maybe if you are fitting something extension of mellow statistics, which is n log rho plus 2 times the number of independent parameters. And there was not a good explanation for what 2 is. And my advisor came with the log n, mk times log n, n log rho plus mk times log n. This is called BIC, Bayes information criterion. But all the statisticians, they never mentioned my advisor's paper. This is a grudge for me. I'm on record, I'm going to say it. He is there, may his soul rest in peace. He will be smiling now because everybody cites the 1978 Gideon Schwartz's paper in Annals of Statistics. It's a short note. It says this, and nobody mentions Kashyap's 1977 full-blown Bayesian way of getting at that, n log rho n plus mk log n, where mk is the number of independent parameters. Of course, there is also Hanan's rule, log n, and so on. This racket was going on at that time. I did that for AR and MA. But anyway, we'll talk about that. So I'm showing off a little bit that I know some statistics. Anyway, okay. This is another thing that's happening, learning on the spectrum. When I was a graduate student, we only had 2 extremes: supervised, you put Bayesian distributions, parameters, and so on, and classify; unsupervised, k-means. We didn't know anything in between. But now we have the whole thing in deep learning. We have semi-supervised, weakly supervised, self-supervised. Self-supervised, because if you have tons and tons of data, there's nobody sitting there and putting labels on them. So you got to somehow cook up from there and then hope you can fine tune. Simple example of self-supervised method. You take my face, put a grid, maybe tiles on my face, and then you rearrange the tiles like a jigsaw puzzle. Tell the neural network, this is Chellappa. You don't have to even tell neural network that. This is the original face. This is the rearranged face with the tiles all over. Can you put it back? I can do the same thing with everybody's face without telling the neural network who we are. The network says, okay, I have to somehow figure out to put the tiles back so it looks like a real face. In the process, it learns something about a face. That is your self-supervised method. It's, potentially possible. And then you fine tune it for various specific tasks for which you have labels, right? So that is where we are going. So just to give you a very quick idea of where AI has been. I talked about neural networks. Of course, people think AI just happened 10 years ago. Not true. It's there in Turing's 1950 paper, Can Machines Think, and also the 1956 summer workshop at Dartmouth that everybody talks about. Some of our best minds are there. They coined the name or the field. And in the early days, AI was busy with playing games. When we were students, we will write puzzles, solve puzzles or all kinds of things. The 3 missionaries and cannibal problems, the Tower of Hanoi problem, are playing, games and so forth. And then it became serious. It was using rule-based systems. Then Bayesian causal models came right around the mid-80s. Julia Pearl, made it nice. And the idea of conditional expectation in terms of being able to write the joint likelihood of a Bayesian network as a product of conditional probabilities and so forth. And then the application areas were always in speech synthesis, speech recognition, and then natural language processing in computer vision, object recognition and detection and so forth, and robotics and so on. So we have had all of this. And of course, your Google map relies on A* algorithm, a classic search algorithm that came in the 70s and so forth. So there are many, many applications, Alexa, Siri, and so on. But what has happened is AI started with domain knowledge, rule-based systems, conditional probabilities that reflect what's happening in terms of dependencies and so forth, and now it's all data. So I like to say that AI tried everything else and finally settled on data. Okay, that's where we are. So there are many, many techniques. You will recognize some of them, heuristic search, the A* I talked about. Clustering is a big component there. K-means, as an example, Bayesian networks, reinforcement learning is important, genetic algorithms. Simulated annealing is also kind of part of. This is a thing that came in the mid-80s, Gieman and Gieman's work. And then, I told you neural networks and AI, they have kind of had a somewhat rocky relationship in the early days, but not anymore. And you have, going from handcrafted features that used to be popular in computer vision to now data-driven features and so on. Very quick case studies. Why computer vision people, or why everybody is clamoring about neural networks, as I said, performance. We built an end-to-end face recognition system for the US government as part of a project from Intelligence Advanced Research Project activity, and we are continuing as a follow-on project. They told us, they said, well, deep learning is working so well, we want the best face matcher you can do, okay? So we went and collected data, they gave us some data, and we built, big face detection, recognition, everything. So it'll detect your face, it'll estimate your pose, it'll say whether you're smiling or not, and it'll give an estimate of your age, it'll give a gender, and so on. And we brought the idea of multitask learning. Okay, the fact is, if you have 101 layers, the bottom layers are very generic. They kind of, attempt a very generic thing. They are not focused on doing the ID yet. So some tasks will have more data, some will have less. So you can share, just like a bunch of you get together and study for your finals, right? Same thing you can do. And the classic loss functions for Euclidean, if you are doing pose estimation or extracting fiducial points on your face, or it could be, cross entropy or softmax if you have a multi-class problem. So these are the classical loss functions, and we built it. I tell you, phase one, IARPA had some metrics. We all matched it. They said, oh, is that so? They made the phase two metrics 10 times harder. That's when I learned, if you are overperforming in phase one, don't tell the people yet, because they make the phase two metrics harder. So this is what happened. We go expecting something, performance will be happy, and deep learning gave so much more. Okay, so, and then there was a follow-on program for IARPA, action detection in untrimmed videos. Typically before that, we do trimmed videos. That means you will have a video, me throwing a ball or catching a ball or doing this or that. Here, no. Things happen in a very large area like a parking lot, 37 actions involving vehicles, humans and vehicles, humans and facilities and so forth. I got to detect, match, and I have to say where it is. So spatio-temporal localization and characterization effect. Again, deep learning was not that successful. It was good when I know the site, when I've seen the actions before. If I change the site, even for the same actions, the performance went down. But if I had to do surprise action, things it has not seen before, it failed. Only 20% success. So take it from me, AI does not like surprises. Okay, that's what sometimes causes accidents with the totally automated cars or anything. So if it has not seen it before, it has issues with it. So we have to keep in mind. And this is a domain shift is something I'm going to be hitting again and again and again. So to me, that is a very, very important issue when we depend on data. So here, what do I have? I want to develop an algorithm that will look at traffic cameras and collect, get it up, process it to say what car is that, how many are in the intersection, and is the car I'm seeing in Inner Harbor is the same car I see in Homewood across city scale. Thousands of cameras. We have data from this. The interesting thing we found is to train a machine to do this. They gave us some curated data, very nice, high quality, high frame rate, no compression effects. And then when I have to apply it on the traffic data, pretty bad. Compression effects, low resolution, low frame rate, domain shift. Every camera behaves in its own way. In fact, you will see there's a camera bias that gets built into these data-driven algorithms. That but algorithm only likes this camera because that's what it has seen. You change it to a different camera, the performance goes down. So domain shift galore everywhere here, right? For every data camera, it behaves a little differently. So what we did, we took the annotations from the high quality data, we dump it down to make it look like bad data. And so we can, transfer, learn, and then make it work on the bad data. Because if it's very hard to make a bad data look like a good data, that's an inverse problem. There's so many things that happen to it. So this is another case study. Of course, pathology, same issue. Every lab has a slightly different way of creating their images and so on. So domain shift, is there everywhere. So statistical methods, when compressive sensing came, 2005 to 2012, L1 optimization became very important in our world. And I always felt, my advisor, Professor Asriel Rosenfeld, he did not like linear models and he did not like Gaussian assumptions. So because signal processing, we always did those linear models and Gaussian, so you can make some analytical progress. So he said, Rama, as long as you are stuck with linear Gaussian models, you are not going to solve computer vision. Yeah, maybe he's right. But anyway, L2 norm is very good. L1 is there. So when hierarchical models are considered, it becomes a little difficult. So anyway, so these are the issues I face. But I also will tell you, if anybody is there to give us confidence that our deep learning methods, our AI methods work, we need mathematical statisticians. What a timely time for Professor Mark Suchard to come. So we need you guys to take a look at what we do to give some kind of confidence for us, because we are all in the empirical world. We just run it and we are 2% better than the other guy. We say we are good to go. But it's not that easy. Non-linearity, hierarchy. So it requires, total revamping of Stat 101 or whatever the initial Bickel and Oxum based courses are. So that's why it's fun. Okay. So, lack of analytical result, it bothers us. Too many parameters we are learning. When I took my pattern recognition class, Professor Fukunaga used to say, if you want to estimate a covariance matrix, D into D plus 1/2 independent components, you should have at least 3 times that to make some, good estimate and so on. When we go to deep learning, we don't care. We have billion parameters. We don't care how much data we have. We just run it. Clings to the data, training data. It allows it. Anything outside that, it gets into trouble. And okay, so we can pile on. Not good. Okay. So these are the things: domain shift, bias, adversarial attacks, lack of interpretability, privacy, maybe it's not there, and emerging dependence on synthetic data. Even a person who's not in AI, if you tell them, oh, we have a problem collecting, oh, why don't you use synthetic data? I said, wait. It's not that easy. Okay. So everybody thinks somehow that we're going to magically take care of all our issues. I'll tell you why it's not so. There is a nice paper from my friend Rich Barniak at Rice University. He calls it, if you use a synthetic data generated by a deep learning and use it to train another deep learning method, he calls it like a mad cow disease. There is a nice paper in NeurIPS, and I'll briefly mention that. And I agree with that. When we do synthetic data in computer vision, we don't use deep learning to do that. We have models. We have human motion model, right? So we can do that. Or we have illumination models. We have scene models. They all come from geometry, from sensor thing, and so on. I trust them more than just letting a synthetic thing that comes from a deep learning. But we are all doing that. So this is a classic. Now, Mark, you are not here. I was telling everyone that since I took 6 graduate courses and they kill me with homeworks, all the statistics professors at Purdue and exams, anytime I have an opportunity to give some problems to statistics professors, I never miss it. So there you go. But you don't have to submit any homeworks. I'm not grading them. This is a classic domain generalization, domain adaptation problem. I have objects collected, I have labels, and then I have objects collected, slightly different posts, maybe even same objects or same classes of objects, mugs, everything. It's called Office 31 data set from Berkeley, from Trevor Darrell's group. And then when in 2008 or so, I was working on iris recognition, the James Bond stuff, right? So I had a nice sensor from LG. And then they called me up and say, Rama, we have a better sensor. It's a little bit more expensive. I've never said no to these kinds of better sensors. So I said, sure, send it me. It was a classic machine learning method, not any deep learning. I take it and I apply it on the new data, much better data, high quality data. Performance went down. I asked my student, check your code. Check your code. No, sir, it's going down by 10%. It's like, I've been drinking tap water everywhere and suddenly somebody gives me a bottled water, I get sick. It doesn't happen, but that's what has happening here. So we said, why? What's happening? That's when we came up with the sensor, adaptation and so on. So this idea of adaptation has become somewhat a very key thing in my life. Since 2011, we have worked on this domain adaptation approaches using various representations. I'll briefly discuss them. This is the first challenge. If people ask me oftentimes when I give general talks, will AI kill us? I said, don't worry. Domain adaptation will kill AI before AI kills us, because we can't give performance guarantees that you take this system and work for somewhere else that is going to give you the same performance. I can't. If it works, yeah, thank you, but there's no guarantee, right? So this first thing we did was we want to unsupervised domain adaptation. Source data, labels are available. Target data, no labels available. So how do you do that? So I said, okay, we learned from our pattern recognition course, if you don't have any labels, you can always do principal component analysis. You can align the data and get the vectors out, build the covariance matrix for both source and both target, and you don't need labels for that. And then you project them onto a Grassmannian manifold. They're sitting on the two sides. You find intermediate, and then you can, develop these intermediate places. And then you can project both source and target data onto them and develop your representation. And then find out which of the source thing is closest to that and give the label to it. So unsupervised domain adaptation works, right? So we tried that. The performance was very low, but the reviewers liked it. We had finite intermediate subspaces, and then PHAISE and Christian Grumman came with a slight modification and came up with infinite intermediate subspace. They call it GKF, generalized kernel flow, and so on. Since then, there have been so many papers on this topic, right? We have done it with manifolds. We have also done it with dictionaries. Dictionaries became very popular after compressive sensing ideas. So we will have a source dictionary, target dictionary. We will project them onto a latent space so they stay close to each other. And we'll also add a discriminative function in the class function and get the representation that will be good. It's almost like somebody mediating between two parties that they don't talk to each other and come up with something common between them, right? We have done it. And we have also done it with generative adversarial networks. We have a source data, and then we will create, we have a target data, we will make it look like source data, because after all, it is a generative model, or vice versa, whichever is better. And we have done that for semantic segmentation, and then we have done it for object recognition and so on. So that is assuming both source and the target data are with you in your left and right hand. Oftentimes, you may have situation where you may not have any source data. So here we take the approach of covering the bases. Get as much of source information with multiple sources and so on, and then put it in a meta-learning framework, domain generalization, and we have a NURBS 2018 paper, and a lot of people are building on that. So that is another thing. Domain generalization is also important. You cannot assume you will always have a target data. So that is problem one. Problem two, given my first 2 years of model order selection rule for time series models and so on, obviously, do you have methods for pruning the size of neural networks, right? Even in the late 80s, you would see papers called optimal brain damage and so on, in the sense that how do you make some neural weights disappear and so forth. If you look at the AlexNet 2012 paper, they also have similar strategies, because people were first shocked. They have been told, you have to build a parsimonious model and this and that, and then suddenly here, even a simple VGG net with 18 layers have some kind of millions of parameters. So it kind of shook people. What is going on here, right? So people want to have some strategies for reducing the size of the network, and also it helps to take deep learning into edge computing. So the models are not that big. But which models are, they look at the weight, values, and this and that. So it's not a very rigorous method. So we need rigorous methods for model order reduction in nonlinear hierarchical models. So that is number two. Number three is, what is there in the deep network? We develop representation. Everything I say for deep learning works for transformer models and similar things. They're just different ways of getting representation. So when I built the face recognition system for IARPA, at that time, 2018, there was this paper from MIT that showed some of the existing commercial algorithms, Amazon Recognitron and other things, were not working very well for working well for light-skinned males and females, but not working well for dark-skinned males and females. So everybody got scared, right? It's AI bias. It became from face recognition bias to AI bias. So we had to figure out what information does my deep learning features have. So how do you do that? There is a technique that's called mutual information neural estimation, MINE, which allows you to go and test whether the face features I build, whether it also carries gender information, whether it also carries skin tone information, and so on. And if you find it, then you can suppress it. Because I designed my network just to verify and recognize an individual. I didn't tell it to learn the gender and the age and all of that stuff. But like in the diabetic retinopathy case, they could look at the features and predict the gender of the person. They said at the 0.97, AUC and things like that, right? So that kind of surprised people. So these deep features surreptitiously learn more than what they were told to learn. I mean, maybe that is good if you think of it as a student, students learning more than what we tell them to learn, but these deep learnings learned for maybe a nefarious purposes. We have no idea. So this is something we do. What we found in the face recognition system in the lower layers, it was focusing on pose, age, and it didn't care much about the ID and so on, gender. But as it went up and up and up, it started focusing on the verification, because that's what we give as a final output. And so, backpropagation comes from the top to bottom, right? So we also saw similar things as a number of iterations. So we need to have a method to see if the representations you derive for your problem has other things in it. And for some problems, what the other things are obvious, like in face recognition, but for some problems, they are not. So we need to think about how to probe the features. So of course, once you know there is a bias, so what we have to do is we came up with methods for mitigation. I tell you, of the many issues I suggested as issues, bias is societally very important. You can't give a technology that will only work for some and won't work for others, right? The question is, will AI work for everyone? AI ethics now is mostly about bias. How do we figure out whether this is a fair system? People often cite Compass, the system that is being used to figure out how many years somebody should be in jail and so on. And they have done experiments with it and say it is very biased. Okay, so if you want the technology to be broadly applicable, we have to be able to measure, detect, measure, and reduce bias. Now, the only problem is, even when I do it using knowledge distillation and adversarial training and so on, I cannot bring bias to zero. Okay, so do I go and tell, yeah, I built the system, but you know what, it is somewhat biased. Nobody wants to admit that. And we don't know what is an acceptable bias. So the same thing happens when you go to medical data, right? You have for one population, and then you try it on the other population, it may not be so effective. So this is problem 4. And anyway, so we have papers on this. If anybody is interested, just ping me and I'll be happy to share them with you. I'm local, by the way, I'm just a couple of miles away. So we can always talk more. So GANs became very interesting right around 2013 or so, generative models. I like to think Markov random fields are generative models, and they are, but they are linear. And for my PhD thesis, I had to share a PDP 1145 with 30 other students. So I created 32 by 32 stamps of generative images. Not very interesting. Okay, that's because Markov, if you have a Markov model, if you have a Gaussian model, you can do it with just simple matrix operations. If you have binary and multinovel and so on, you have metropolis sampler, GIF sampler, and so on, you can build images. So you can go back and look. We were working on textures analysis. They were not good for actual picture like a face and so on, but textures it will create. So because they're linear also. And I never went more than 12 parameters in my model. Third order Markov is all I did because I have 32 by 32 image size, and people will say, hey, how can you go and have 100 parameters for this? Well, you never took a statistics course? That's what I will hear, right? So, okay, I only stuck with 12 by 12 and, it tried its best, poor thing. It is not, now we have billions of parameters in all the generative models. So it does do well. Anyway, so GANs came, and for a couple of years, 2-3 years, GANs were there, of course, variational autoencoders and all of that. So we use GANs for domain adaptation, actually. We will use GANs to bring the source and the target to a same place, so they will do well. And then we have, they are useful for all kinds of things we have done. I'm going to skip that. But now we have diffusion models are really coming into picture. So I take a picture, and then I add Gaussian noise to it. Gaussian, a series of transition probabilities. So there is, despite what my advice mentor, Professor Asiel Rosenfeld said, there is Gaussian sitting everywhere in the diffusion model. So we add noise and noise, and finally we make it look like totally noisy image, and we learn the forward process, and then we reverse it to get back to the original image space and build. All your beautiful pictures like this you see, they're all from denoising. I tell you, 1981, if you tell me that using these kinds of Markov, diffusion, etc., I will be able to do it, I would not have believed it. So this is where you see NVIDIA doing beautiful things like this. One of my former students is a director for research, and I say, why are you doing this? He says, sir, we want to get everybody interested in so people would buy more cards, GPU cards. You really need GPU cards to make them work, right? So these are beautiful pictures and so on. So generative models, similar ideas are there in ChatGPT. So what is the issue here? Hallucination. I have no idea what it will generate. The Google's Gemini is a case in study, right? They have to put a pause on it because sometimes it may produce something that we didn't anticipate. Now, not all hallucinations are bad. I sometimes say good hallucinations are imagination. Sometimes we think of weird things and write a paper about that, and it breaks open something. But we don't know what is a good hallucination, what is a bad hallucination. Again, statisticians can do that. So when you look up a large language model, at some point, it's all about embedding. So embedding is like a data for you. So you have to be able to look at the data and say, hey, is there a small probability that it will do something weird? Okay, I think that is something that we need. So they're being used everywhere, as you know. Other thing, there's a lot of data. If I am Meta, Mark Zuckerberg said he's going to have 600,000 cards this year, by end of this year, 6 billion. I have 300 cards, but not as powerful as the ones he has. 3090, 4090, 5000, 6000, A40s, and so on. 48 gigabytes is the maximum thing I have. And in return, Microsoft and OpenAI says they're going to invest $100 billion cluster recently. You need all of that for training. Okay, fine. But do I really need all of it? Is there a best way? I have a classifier now. I know it performs this well. And I have a 10 million data set, mini batch. I want to send 1,000 at a time. Which 1,000 should I send? So we looked at that problem. So we came up with a criterion function. What happened? I had all of those slides, but I got an email saying my talk is 30 minutes. So I removed some of those slides, but that's okay. It's all there. But I hope you get the message. So we had to take into account what the current performance is. And then out of the 1,000 things, how I have to spread it across the various classes. Balancing is important, so it is not biased and so forth. And we wrote a function and then used a watershed algorithm, the information theory, it is popular, to come up with the optimal way to, check that, right? So when we did that, in the early stages, it will keep good faces. And as we were doing it, it will bring in more and more difficult faces, as you can see in the bottom row, with the funny thing on the nose and the hat and all of that. So there is some kind of a curriculum learning thing you can fit into this. That means you start with easy examples, let the machine learn, and then you give more difficult examples. So we had some fun with it. The other thing is, we have data everywhere, but people may not be interested in sharing data. So, but they may say, okay, we'll give you our models. How do you federate the model? Right now, we still think people are averaging. That's what is happening in my world. So we need probably better ways. And there are a couple of recent NY Times article, right? How all these big companies, they sometimes, I'm only quoting the New York Times article, it's not me, that big companies will just grab data wherever they can. And sometimes they say, well, if somebody sues us, we'll worry about it later. That's what the gist of this article is, right? And then there is a nice paper from the HAI, the institute at Stanford, rethinking privacy. And privacy is important. Everybody worries about it. But I think one thing we could do, maybe statisticians will show us the way how to learn from totally anonymized data. What can you learn? How much can you learn from there? And then federated learning means that definitely domain shift is there. There are different nodes, different models, different data. So how do you handle that? When they won't give you data, you can't measure how much there is domain shift. If I have source data and target data, I can do Wasserstein distance, I can do MMD from Professor Michael Jordan. I can kind of tell you that, oh, this is a lot of shift compared to this. But if I don't have your data, I won't be able to do. So how do you do that and so on? Robustness and even security-wise. Some models may be more secure than others. So this is a big area and definitely makes sense for the medical space. This is a classic thing now. There is thing saying, okay, in 2030, synthetic data will complete. I don't know, people make all kinds of projections, right? In fact, I saw somewhere in New York Times and 42% of the CEOs think that AI will wipe out the humanity in the next 5 years. I said, oh my God, I need to talk to those people. Yeah, so all these predictions are made. This is synthetic data. I'm not against it. But there is domain shift. The moment you do synthetic data, it's different from real data. So how good it is and how we are going to manage that. We do use synthetic data for a problem. Yeah. Anyway, we have people doing actions. We have ground-based cameras. We want to do them from UAVs. There is big domain shift, geometric shift, for example. We have a lot more data from ground-based cameras, not much data from UAVs. So we actually generate synthetic data of people doing these actions. But we don't use deep learning. We use models of humans doing all these gestures and actions and so forth. In fact, the problem I mentioned before, DIVA, we have 37 actions, and we, as part of an Army research project, there was a company that was hired to synthetically generate even multi-person, multi-entity actions. People working with their vehicles or people getting in and outside of buildings and so forth. But none of them were on synthetic data generated by deep learning machine, right? I trust them a little bit more. They're more expensive, but they have precise models of everything, okay? But you cannot generate too much. The reason why people like synthetic data, annotations come free. When you create it, you know how you produced it. So for semantic segmentation, if I have to have training data at each pixel of a picture, I need to say what that is, a vehicle, a fire hydrant, a shop, a building. It takes time. But I can use, Grand Theft Auto synthetic sequence for segmentation, or Cynthia data set and so on for segmentation, synthetic to real, but domain shift is involved here, right? So you can't just trust that synthetic data is going to take care of everything. I deeply, deeply worry how it will work for health and medical. It's not easy. It's one thing for me to do it for computer vision problems where I understand the objects, their structure and so on. But in terms of synthetically generating, something in the health domain, but the concept of digital twins is somewhat like that. And it's becoming more and more popular even in medicine, right? So, this is a nice paper that came from Rich Barney's group at Rice. So they looked at the process of using a deep learning machine to generate synthetic data and train another deep learning machine. And they called it mad cow disease kind of a thing. And they did a lot of experiments and showed how often you should inject real data, or can you just do with all synthetic data and so forth. I think in the case of, self-driving cars and so on, a lot of synthetic data is being used, but also a lot of real data is being used. There's Waymo data set is pretty large and so forth. So this is something to keep in mind. What role will synthetic data play and so on. The last thing, when I was working on my PhD thesis, I came across a paper by Doug Martin, another University of Washington professor, robust estimation. He was working on it a lot, and he actually had a very nice Journal of Royal Society Series B paper talking about this and so on. So I got interested in that. Then I went and read about Huber's work, and we actually worked on robust models for two-dimensional random fields, spectral estimation and so forth, using, I think in one of the papers we looked at the influence functions for 2D Markov random fields and so on. So there is some synergy, between adversarial attacks and robustness issues, right? Adversarial attacks, basically what happened, I have the two picture of a truck, right? Okay. And in between you have that noisy pattern. If I add that pattern to the truck in the left, then the machine will think it's an ostrich. This 2013, Google person showed these things happen. So this immediately opened the floodgates of all the cybersecurity folks got so excited. All we had to do, take a panda, add something to it. Oh my God, it becomes a gibbon. Oh, okay. Or you take something umbrella, then it becomes a rifle. NURIPS was full of these kinds of papers. So there are many, many different attacks. There is a noise attack, there is semantic attack, there is the FGSM attack, there is PGD attack, there is Carlini-Wagner attack, and so forth. And I kind of felt a little sad because all the examples were from computer vision. I said, it took 50 years for us to make computer vision look like it's working. 2012, AlexNet showed deep learning is going to work. And we said, okay, finally, computer vision may be useful. 2013, people attack it and say, well, you just add a small amount of noise. Visually indistinguishable to human eye, but AI will call the second one, attack one, totally different. It really depressed us. But, that's reality. Why is that? Because again, it's nonlinear and nobody said because it works well that it has to be also very robust. I mean, those are separate things. So we came up with some defense methods using GANs, generative methods to kind of figure out if the image has been attacked, and then we smother it and then send it to a classifier. Very much like what you would do in the case of robust statistics. You have outliers, and then you use Tukey's redescending function or something like that and kind of smother it. And then it leads to either weighted least squares methods or, generalized M estimation and so on. And this has been done for time series models, regression models, and so forth. So that we were motivated by that. There is a lot of work that's going on here. We have various kinds of attacks now, We can actually use large language model to attack. I just say, okay, add, snow to this car, do this to that thing, and so on. And we can do that, and we can create all kinds of variations, okay? So I'm just going to close with recent trends, meta learning, learning to learn, weakly supervised, semi-supervised, self-supervised, and of course, generative models. But what is needed is to make everything we do in deep learning these days to come with some kind of a guarantee. Of course, there are papers that talk about certifiable robustness and so forth, but we are only able to consider very simple models. The models for which we can provide theoretical guarantees don't work well in reality in terms of giving performance. The one that gives performance has zillions of parameters, layers, and so on, for which we have no performance guarantees. So there's this big field about trustworthy AI. Trust has to come from statisticians. Whether you think it is worth your time or not is a different story, but there is plenty to do there. So, for regress, we need regress methods. Okay, there's a lot of alchemy now. We still do using benchmark data sets and so on. Alchemy, who knows? Once in a while, it may produce gold, and we are happy with that. But we need you guys to clean this mess up. All right, thank you.
Some time for questions.
Can I start with that?
Yeah.
I really appreciate your last comment, and I'll say, I feel tension in this, and it's really great to have you saying it because you come from this world. Because I worry sometimes that statisticians come across as sort of just the gatekeepers of sort of like, oh, well, you have bias, or oh, there's this problem or that problem. So do you have advice for us in terms of how to help? Like, I really appreciate your words around this, around trustworthiness, et cetera. Could you just talk a little bit more about sort of how you see the AI field moving, or like, are there things that we could be doing to sort of help? Basically, how do we help others sort of understand that, but without coming across as just the, again, sort of gatekeeper?
I think sometimes I have the same problem when I talk to people in AI ethics. I tell them, whenever I talk about AI bias, I said, don't just talk about AI bias, also mention what that is being done to mitigate. So there is a balance. Whereas if I just focus on, putting AI bias, shame, we have, then we become, we're not listening. So every time I'm on a panel, I always say, I agree. I have this problem where I saw this, but I'm also trying to fix it. I cannot reduce to zero. Because if I reduce bias to zero, I have to reduce the data so much, I have to change. The whole performance goes down, nobody's going to use. But how will I go and say, yeah, you said it's bias, be careful. That is the issue we have. I tell them, don't just scold us. I said, we also are trying to mitigate. We're happy that you told us it's biased. But you know what? Stat 101 says when you add noise in a linear regression model, your least square estimates are biased. So we have bias compensated least square system. There's something called errors in variability, which Besag actually did for Markov way back in 1977. So it's not like.
Can you stand close to the mic?
Yeah, right. So it's not like I think this is how you should do. You tell us, Rama, I think it's like you should talk like a doctor to me. You say, I looked at your reports. Don't worry. You have a little bit of elevated this, elevated that, but we can take care of it. We can help you. You just have to take this medicine for a few days, 3 times a day, and drink a lot of Diet Coke. And you will, or maybe cookies. Eat some cookies, you'll be happy. So you'll be okay. Don't worry. I want to work with you because it's an important area for me. I'm trained. You are trained. I was telling, I'm not saying this just because I'm with the statisticians here. You guys are the, performance guarantors or whatever, right? Right? You calculate the variance for everything. You calculate probability of error for this. Of course, things get a little dicey if it's nonlinear, if it is non-parametric and all of that. I say again, I had to go back to my pattern recognition. Pattern recognition is a great field that brings statistics into it, right? If you have a Bayesian classifier, it's very easy to evaluate the error somewhat, integration and so on. You immediately go to non-parametric method, k nearest neighbor rule, fix Hodges and so on. It's the 4 pages of derivations. And I always felt anytime you go from parametric to non-parametric, life gets harder. So that is how you should complete the sentence. Don't say, Rama, you have bias. Rama, you have bias, and I can tell you how to reduce it. Then we are listening because we are also struggling. That's the way to do it. Yeah.
Thank you. And I think you've given a lot of dissertation awards for all the students or ideas for all the students. So thank you.
Oh, there's plenty for statistics. Yeah. Mark, please.
I think you highlighted almost a dozen different problems with some great examples and some work that your group and others have been taking on these. They range from differential misclassification to hallucination through synthetic data and reinforcement. For the students in the group, what do you think is sort of the most pressing problem in AI in general? And what would be the most pressing problem for people interested in public health and attacking these types?
2 questions you should be able to answer. Will AI work everywhere? Will AI work for everyone? Those are the 2 questions. Unless we can, that is, of course, I'm framing it in a very high level way. So if you can take a popular method, for example, let's say you can take an LLM, look at the embeddings. We're all saying, right, Gemini has to be paused because it does stupid things sometimes. I want to calculate the probability of that doing it, starting with embeddings and what is the probability it will stay within its domain or maybe outside this much. Put circles around circles, and see where is the probability. And if it turns out your LLM is going to hallucinate more than mine, then I won't use yours, I'll use mine. So those are the kinds of things. So when we look at eventually numbers go into this, right? I mean, it's a deep learning, it's an optimization sort of thing. So we may start with language and so on, but we're always looking to embeddings, and then the embeddings go where we make inferences, right? That the other thing is, why do we believe just because we learn we're a very, very large data set, everything should be fine? How large should data be for me to achieve this? In a simple IID, mean estimation, sigma square by n is the variance. We say, oh, okay, if you have this much of n, you're going to be due. There's nothing like that in deep learning. So give me some guidance. Okay, for this network, if you want a classification accuracy to be within blah, blah of that, then maybe you need, 4.3 million data from this distribution, or something like that. I mean, it's hard. The reason why I say it's hard, my experience from 1982 work, I ended up writing a chapter on that. That's the nice thing being a professor. Even if you don't know, you can just write a chapter on that, right? Book chapter. I did it in 1982, time series models, multi-resolution time series models. I quoted some results from econometrics and so on. I said, this is hopeless. Wavelets are much easier. Again, that's a great example. You want to put a stochastic model and try to explain everything, or just go and take some transforms with the wavelets and be happy. There is a version of that in the neural network called scattering networks by Stephen Mala. Five layers, beautiful theory. But 5-layer thing doesn't produce results on ImageNet. You got to go much deeper for the problems we have. So this is the issue. So students can take a particular popular algorithm like diffusion models. What is the probability the diffusion model will create something that's outside what it was trained on? And you know what? Why you can do that? It's all conditional densities are Gaussian. T of xt condition xt minus, it's all Gaussian. There is the beta parameter that floats around and so forth. So it is very much within I like to say, my students actually, don't go to non-Gaussian. Life is miserable. Do mixture of Gaussians. Because you still can leverage something from the Gaussian thing, expectation maximization algorithm is a great example. It all looks like Gaussian, but a little bit complicated. A few of them are there. In fact, we have a new method called neural radiance field, given images how to build models. There's a method called Gaussian splatting. Lots of Gaussians sitting there. And, Gaussian is like a familiar uncle. It's nice, friendly, right? We can do something with it. So that is what I will advise. Try to take diffusion models. That's very much in your thing, stochastic process. And then it does produce the forward, reverse. And I'm sure we're not seen the last of it. In fact, analysis-wise, we are at a very, very beginning stage. Brian.
Yeah, thank you so much for the talk. And I'm sorry, I just sent you a bunch of emails asking you to do stuff. But I also lamenting the downfall of models and symbolic representation. And I'm wondering, in computer vision, what are the chances that symbolic representation of models are the right way to go? They're just harder to develop, and it'll take longer to get them to be performant. And that maybe we're taking the easy road instead of the correct road. And then this follow-up question is, can AI help us build better models and symbolic representations?
That is the hope. For the first question, I feel if I integrate the domain knowledge into my algorithm, I don't have to depend on so much data. That is where I think these two things can come together, But right now, I actually have a paper a few years ago where I took the traditional wavelet-based object detection methods and set it in the context of backpropagation and so on. I call it blended learning. Something from the old, something from the new, and put it together and show that there is a profit advantage of doing that. I think the way computer vision now is, we have kind of lost our way a little bit. I mean, people would say, Rama, you are an old guy. That's what you're going to say. Right? It's not that. I mean, who doesn't like a performing system, right? Eventually, that's what they say. So that's the problem now we have. I think we have to have more examples of bringing in domain knowledge into our algorithms. But you know what? When you go to public health, domain knowledge is very important. You can't avoid that. When you go to medicine, public domain knowledge is very important, right? If you say domain knowledge is not important, then we don't need doctors. We don't say that. Somebody has to look at it. So I think eventually, I hope we have more examples of these blended methods. Take the traditional methods and create a learning framework for them so that it can exploit data. You know, we have reached a kind of a point of, I don't call no return. When physicists want to develop rules from data, right? I mean, physics rules, I thought God given on a tablet, but then now they want to, that is happening actually, because some things are so complex. The whole idea for Metropolis sampler came in the 1950s for a reason, right? It was a very complex behavior they are trying to simulate, so they went with that. So you are going to have this, believe it or not, 2008 time, some framework at Indian Institute of Information Technology actually gave a talk. If you don't have data, go with the models. If you have data, throw the models. I have the slides now, so that's what I said. I have no idea why I said that, but I'll give you an example. We built methods for structure motion estimation, moving objects in a scene. We modeled the motion. We assumed it to be constant velocity, precession, this and that. That's the electrical engineering style. Professor Takeo Kanade at CMU, he looked at all of that and said, Rama, it's too complicated. He just modeled the transformation between frame to frame to frame for a long sequence. And then he built the data matrix, XY coordinates of these points. And then he figured out it has a rank of 3. And then he factorized it using SVD, shape matrix, motion matrix. But it was for orthographic projection. That means the objects have to be way out there. I was looking at perspective projection all the time, so I had not some ratios and so on. But somebody extended it. I mean, to me, that is the first example of a purely data-driven method for structure for motion. He didn't assume any model. He said, well, there is a rotation, there is a translation between the frames. And so I'm going to go with that. So so there you can see not having the model, but then there were assumptions too. It's only for orthography and then it had to be more complex for perspective projection and so on. I believe domain and data working together is where we have to go. That will provide some scope for performance things, that will provide robustness. Adversarial attacks will not be so damaging. People can't believe that two visually indistinguishable images, one of them can go to a totally different label. Okay, I actually have a method. For example, you want to put your face in your website. Can somebody download it and use it for training a face recognition system? How do you avoid that? Sometimes people will wear some goofy glasses and then put that thing because that will kill the face detection algorithm, so they can't download. But we developed a method, it's at a review, where you can keep your original face, but when somebody tries to download it, it will look like a skunk or a tiger or an elephant, whatever your favorite animal is. We can do that. So you protect privacy, right? So all of these things are happening. But to answer your first question, I think we need that second. What was your second question?
Assuming that models are still important, that can we use AI to do better models rather than AI directly going for the goal of better performance?
I remember I talked about, is there a Bayes information criterion for choosing better model? There's something called neural architecture search, NAS, but it's empirical. We have done some work on that, and Alan Yule has done work on that. Many people, if you have so many different models, which one you should use? It's empirical. We don't have. Can AI develop a model? I would say, when you take a self-supervised approach and then you fine-tune it, the final model is an AI model, and AI is kind of helping you to do that, right? Yeah, that's a good question. I don't have a great answer for that, but neural architecture search is an active area. Yeah.
Burning question from the Zoom.
No, just thanks. And I want to say we had 70 people on Zoom at one point, so great attendance.
Thank you. Thank you again. That's